It's been said that simplicity is the ultimate sophistication. Infinite Valve Control Systems has developed a new variable valve timing technology. This mechanical approach is strikingly simple, consisting of just four basic pieces. Yet with them, the IVC system is able to generate sophisticated changes to valve timing. Variable timing in opening and closing valve events, along with variable lift and duration, can all be achieved. With electronic controls, the IVC system even provides engineers a way to enact separate valve timing events for each cylinder. The animation accompanying this video is intended solely to illustrate the basic concepts of the IVC technology. While the animated drawings are rudimentary and do not reflect any refinement such as rollers or guides that would be incorporated into a production engine, they do serve well in defining the basic motions of the system. It is well understood in engineering circles that the camshaft component in an engine's valve train has major shortcomings. More precisely, the camshaft, because of the way it is deployed in traditional valve train systems, is unable to deliver valve timing events that can maximize an engine's power and efficiency. The IVC system overcomes the limitations of the camshaft by replacing one simple machine, the lever, with another, the inclined plane. The breakthrough of the IVC system is that valve movement is controlled primarily through the mated angles of the two key components, not by the slope of the camshaft lobe. For the past 140 years, engines with traditional valve timing systems have been limited because all valve movement has been dependent solely on the camshaft lobe. With the IVC system, a whole new set of coveted valve timing events can now be produced. These valve timing events dramatically improve an engine's power and fuel economy, while at the same time reducing exhaust emissions. The system offers three basic configurations: the non-variable IVC1, the partially variable IVC2, and the fully variable IVC3 format. The non-variable IVC1 format contains just two components, the drive ram and the valve activator. The cam lobe initiates the movement of these pieces, pushing them in a forward horizontal direction. Once the valve activator contacts the wall of the cylinder head, it is prevented from further travel in a horizontal direction. As the drive ram continues to move, the mated angled surfaces of the two pieces cause the valve activator to travel downward, forcing the valve to open. Once the camshaft lobe rotates to its apex, the valve is at maximum lift. Note that at peak lift, the drive ram is approximately halfway up the inclined plane of the valve activator. Once the valve is fully open and the camshaft rolls past its apex, the drive ram reverses direction, moving down the slope of the valve activator, and with pressure from the valve spring, both pieces return to their starting positions. The partially variable IVC2 format is identical to the IVC1 except for the addition of the valve opening adjuster. The opening adjuster can either advance or retard the crank angle degree at which the valve begins to open. Advancing the valve opening point is accomplished by shortening the distance the valve activator must travel before it contacts the opening adjuster. Note that in this advanced timing setting, the drive ram is pushed further up the inclined ramp of the valve activator, increasing peak valve lift. Retarding the valve opening point is achieved by lengthening the distance the valve activator must travel before contacting the opening adjuster. The fully variable IVC3 adds a fourth piece, the valve closing adjuster. This element enables the IVC system to achieve extensive delayed valve closing events. The geometry of the IVC3 components enables the drive ram to go fully on top of the valve activator. When this occurs, the system has provided maximum valve lift. Once the valve is fully open and the drive ram has reached its furthest horizontal movement, it reverses direction and travels backwards with the valve activator. The two pieces travel together until the tangs of the valve activator and the closing adjuster come into contact. Moving the closing adjuster so that it increases the distance between the two tangs further delays valve closing. Conversely, moving the valve closing adjuster to shorten the distance between the two tangs reduces the delayed valve closing event. The preceding animations showed an overhead cam engine design, but the IVC system can also be arranged in a cam-in-block format as seen here. The IVC technology can be deployed in both gasoline and diesel engines, large and small.